Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 2nd, 2025, and this paper came out about 3 days ago. The headline result is a physics-driven avatar system that boosts simulation success from 37.6% to 100%, while cutting per-frame simulation time from 170.0 seconds to 1.1 seconds. The paper is titled MPMAvatar, Learning 3D Gaussian Avatars with Accurate and Robust Physics-Based Dynamics, and as we'll see later, the results are really impressive. Beyond speed and robustness, the method delivers higher fidelity rendering and more accurate garment dynamics, even generalizing zero-shot to new scene interactions. Also, the authors shared a GitHub repo with the full MPMAvatar implementation. You will find the Warp MPM simulator, 3D Gaussian rendering code, and training scripts for appearance and material parameters, plus pre-processing, simulation, and evaluation tools. The README guide setup, data prep, and end-to-end usage with a runnable demo. Alright, the previous segment highlighted the code release and end-to-end tooling. Figure 1 presents the story visually. Multi-view video frames feed the system, which reconstructs a 3D Gaussian avatar. The center panels show novel pose driving, where the dress moves plausibly because the physics model handles cloth contact and deformation. The right panels illustrate zero-shot scene interactions, like sitting and passing through particles, showing robust dynamics and photorealistic rendering from free viewpoints. Well, Figure 1 showed the system in action, and Figure 2 presents the pipeline that makes it work. The left panel depicts a hybrid avatar, where a mesh carries physical parameters and 3D Gaussian splats attached to faces for appearance. The middle panel illustrates garment dynamics driven by a material point method with an anisotropic model, so cloth deforms differently along fabric directions. The right panel details collision handling that transfers normals and velocities with B-spline weights, and then projects relative velocity. Blue, green, and red arrows indicate body motion, garment motion, and collision regions. Alright, Figures 1 and 2 laid out the system in pipeline. Figure 3 compares visual quality across two datasets, with our method placed between the Phys Avatar baseline and ground truth. The left block shows actors' HQ subjects, where sharper textures and recovered folds appear, so wrinkles and pleats align with the reference. The right block shows 4D dress results, which again demonstrate cleaner knit patterns and fewer blurry regions. The pink zoom insets highlight fabric details that remain crisp and physically plausible. So the previous figure showed sharper visuals. Table 1 reports the numbers. On actors' HQ, the method leads with lower chamfer distance at about 0.42 times 10 to the minus 3, higher F-score at 96%, and better appearance with LPIPS near 0.033, PSNR around 32, and SSIM about 0.96. The ablations drop performance, which signals anisotropy, physics, and quasi-shadowing all matter. On 4D dress, the method again wins, reaching PSNR around 34 and SSIM near 0.978. Okay, the previous figure quantified visual accuracy. Table 2 reports robustness and efficiency on actors' HQ. The table lists success rate and per-frame simulation time, which together capture stability and speed. Phys Avatar reached 38% success with about 170 seconds per frame, while the proposed method reached 100% with roughly 1.1 seconds. The jump reflects the fast feed-forward material point method simulator handling collisions reliably, so runs finish consistently rather than stalling. So the previous table covered robustness and speed. Table 3 examines physical plausibility and contact quality. The table reports penetration depth and a learned plausibility score, which together indicate collision handling and realism. Penetration depth drops from 0.294 millimeters with Phys Avatar to 0.047 with the proposed method, showing far cleaner contact. The plausibility score rises from 1.78 to 1.83, close to the ground truth upper bound of 1.86, so dynamics look physically consistent. Wrapping up, two takeaways stand out. A material point method with anisotropic cloth modeling and mesh-based collision handling delivers accurate, robust, and fast garment dynamics, and 3D Gaussian splatting preserves photoreal detail across free viewpoints. The broader implication is reliable, zero-shot digital humans for film, games, telepresence, and simulation. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.